Welcome to part 3 of lecture 2 for nuclear forensics. This is the third part of the lecture on radiochemistry in nuclear forensics. The readings for part 3 of lecture 2, same chapter, chapter 2, physical basis of nuclear forensics analysis in the nuclear forensics analysis textbook. Part 3 will cover the fission process. In the fission process, the fission products of the isotopes that we're most familiar with, uranium and plutonium, undergo an asymmetric mass distribution. And that asymmetric mass distribution is shown here. And this is for uranium-233, uranium-235 in red, and then plutonium-239 in blue. We see that there's a high peak, which is consistent. That mass doesn't tend to change for the different isotopes. This lower peak, we see that the peak increases with A. We have a mass distribution ratio of high to low of about 1.4 for uranium and plutonium. And these peaks, as we've discussed earlier, they're due to shell effects from the magic numbers. The peak is close to 132, which is the doubly magic 50 proton, 82 neutron, so that'd be tin 132. Symmetric fission is suppressed by a couple orders of magnitude relative to asymmetric fission, and this is all due to shell effects. In nuclear reactions, this can also occur, and the fission will compete with evaporation of nucleons in the region of high atomic numbers. So in other words, if you make an isotope from a nuclear reaction, it can undergo fission once it's formed as opposed to de-excitation by, for instance, emitting neutrons. We'll discuss this a little bit more when we talk about nuclear reactions. So as we've seen, the location of the heavy peak pretty much remains constant for the uranium isotopes and the plutonium-239. We see the lighter peak increasing. We can also see an influence of neutron energy, as what's seen here. This is for the 235 uranium fission yield with difference between thermal neutrons and 14 MeV neutrons. The obvious change is that as we increase the energy, this middle section, the yield goes up. What we're seeing is that we're kind of washing out some of the shell effects with higher energy. As we've already seen for uranium-233, uranium-235, and plutonium-239, the fission yield distribution actually varies with the fissile isotope. With the previous isotopes we mentioned, the uranium and plutonium isotopes, that fission yield distribution was rather small. But we can imagine, as what's shown here, as I start to increase the mass of the fissioning nucleus, the heavy curve remains constant and the light continues to increase. We can imagine eventually that, particularly if we get at a close where Z is equal to 50, so Z being equal, where Z would be equal to 100, so that the fissioning isotopes would have a Z of 50, which is here. Fermium's a Z of 100. You can imagine that here we'd start getting symmetric fission. So if we look at fermium, as the mass of this fissioning system increases, the location of the heavy fission peak will start to coalesce with the light fission peak, and we can see areas on this curve where we're plotting N, the number of neutrons, against the mass of the fission fragments for the different, Z is plotted here. These are the different isotopes. We can see that those in the circles here are all symmetric. So we can definitely understand that the fission distribution is actually a function of, we've already shown it's the energy, but also the fissile isotope that's undergoing fission. Another aspect of fission products is how they are distributed. We've already talked about the yields being different, but even within a yield for a given isobar, for instance here the data is for A of 141, we have yields that can be either for specific isotopes, those are the independent fission yields, or the data that we see in the chart of the nuclides, the cumulative fission yields. For the most part, we've been working with the cumulative fission yields, which is an integration of all the independent fission yields for a given isobar. As we can see, the independent yields need to be determined for specific nuclides. These can be difficult to determine, especially with radionuclides fission products that are relatively short-lived. The data for both the independent and cumulative fission yields can be found at this web page listed here. You can find that you'll see that there's actually a relatively smaller amount of independent fission yields available. So the difference between the independent fission yields are shown here, where you have the dots on the line, and the cumulative fission yield is just the integration. And the cumulative fission yield, those are the data points that are available to us in the chart of the nuclides. We've previously described the distribution of fission products as a function of isotope. Now let's evaluate what actually happens with the nucleus as fissioning occurs. This is shown at the bottom of the figure, where the nucleus undergoes a change and eventually reaches a point where it's no longer stable. Imagine if we have charges, protons build up into the semicircular aspects of this nucleus. That charge eventually overcomes the adhesion due to nucleon-nucleon interactions. This is called the saddle point. And the rate of change of Coulomb energy is equal to the rate of change of nuclear surface energy at this point. And this induces that instability which drives the breakup of the nucleus. Beyond this point, we have fission. We have the scission point, where the nucleus divides into two fragments. The high charge in each fragment accelerates the particles away from each other, and we get about 90% of the final kinetic energy within a very short period of time, 10 to the minus 21 seconds. The energetics of the fission process, that's what drives nuclear fission, but it's also something that we can use to evaluate which isotopes will fission and which ones won't. Fundamentally, any nucleus with an A greater than 100 can split into two approximately equal size with resulting energy. However, why do we only see fission at about 230? Because the separation of a nucleus is hindered by the Coulomb barrier. You could treat this barrier as penetration, what the particles would have to overcome in order to form two particles from a nucleus. So if we could figure out the energy from fission and compare that to the Coulomb barrier, we could evaluate the difference and find out where this fission is possible. So we would actually have to have the fission overcome the Coulomb barrier. It just turns out around uranium, both these quantities have values close to 200 MeV. The Coulomb barrier is close to 200 MeV. Fissioning is close to 200 MeV. And once the fission energy is above the Coulomb barrier, this event can occur. For comparing Coulomb barrier and fission energies, we can use our generalized value for the Coulomb barrier. Here we have the two equations. We'll use this equation for the calculations, and all we're going to compare is the Q value for fission versus the Coulomb barrier from the calculated fission products. So here we assume a symmetric fission, uranium going to two palladiums plus some energy. The Q value is 190 MeV, and the Coulomb barrier is 175. Again, for this symmetric fission, which we know doesn't occur, we see that this is energetically favored towards fission. Let's evaluate something more realistic, asymmetric fission. So we have uranium-238 going to barium plus lanthanum. The Q value is, for that reaction, is listed here, of 175. The Coulomb barrier is 164. We see that both these values result in fission. The realistic case, we need to consider shell effects. However, fission, we can also see that if there was not the shell effects, fission would actually favor symmetric distribution without the shell effects. The energetics would be more favorable. As an example, at 200 mercury has a Coulomb barrier of about 165 MeV between selected fission fragments, while the fission energy is around 140 MeV. So this, obviously, the fission energy is less than the Coulomb barrier. Mercury 200 is not expected to fission. The fission barrier is lower for uranium when compared to the mercury, so fission occurs at this point. The Coulomb barrier height increases as we go from something like mercury to uranium, increases more slowly than the increasing energy of the fission. And for this reason, spontaneous fission is only observed among the heaviest elements because the barrier for that spontaneous fission is lower. Generally, half-lives for spontaneous fission decrease rapidly with increasing Z. And here we see two figures where this demonstrates the half-life generally decrease with increasing Z. Here, as we go from thorium, uranium, plutonium, curium, californium on to element 104, we're plotting the half-life versus Z squared over A. But we see that as we go heavier in atomic number, higher in atomic number, heavier in mass for given elements, we tend to see a general trend. However, for a given element, for instance, if we evaluate fermium, if we go to 258, from 244 to 258, we see that at 248 and 244 approximately the same, very short half-lives, and there's a high half-life peak at around 250. And this trend is repeated for the other elements. Here's another example of how we see the half-life change as a function of neutron number for elements paired, grouped into their for isotopes grouped into their elements. And we definitely see this trend as we go from uranium down to element 108. We see a definite decrease in spontaneous fission half-life. A final example of fission has to do with that's induced by other particles besides a neutron. And here we have an example of proton-induced fission. We see a fission mass distribution for the reaction of thorium with a proton that produces this fission product, and here the fission product distribution for the reaction is a function of energy. And what we see is that the excitation, there's a definite influence on the fission product distribution with energy. As we see, we go from 13 MeV protons to 53 MeV protons. We start off at 13 with what looks like a typical two-humped fission distribution, as you would expect for something like thorium based upon the shell model. We're all the way at 53. We see that we get symmetric fission, which tells us that the ground state, lower energies, is really dictated by the shell model. And if we can overcome the shell model, we tend to see symmetric fission. And the amount of energy put into the system by the proton, 53 MeV, is enough to help overcome the shell model and allow symmetric fission product formation.
Parts 1 through 3 of Lecture 2 are to be treated as a review for those of you who have seen the material before, and for those who this is new, it's an introduction to some of the terms and concepts. The history of radiochemistry research was provided. A discussion of nuclear properties, including decay modes, and some equations on the growth and decay of radionuclides were presented. This will be provided in more detail in the following part of Lecture 2. Reaction energetics were discussed. The shell model was discussed. This provided information on magic numbers and how nuclei obtain spin and parity. The relationship between spin, parity, and decay was presented. Nuclear reactions were evaluated, and a discussion was provided on the fission process. When you have completed Part 3, please continue to the summary lecture, the fourth part of Lecture 2. In the summary lecture, the information that will be utilized in the course will be discussed with examples of how the information can be applied to nuclear forensics.